3, we're going to talk about the logarithmic functions. And again, here are the homework exercises from this section for you. Again, I've highlighted the ones that you're actually doing for your homework. And you can take a look at this page later on. But I'll be looking at exercises from this page. I believe this is what page? Page 803 of your textbook. And again, these are the exercises that we will be looking at. Well, not in the highlights, but we're going to be looking at the ones like the highlights or your homework problems. Okay, so let's get started here. Now, in section 12.2, we talked about exponential functions. Remember, the exponential functions are functions that are in the form a to the x, where a is a constant, right? And a has to be positive, and a had to be a positive number. Let me adjust my screen here. Okay. So the question is, if you recall, by the way, exponential functions are one-to-one. So the question is, well, does this have an inverse? Of course, the answer is yes, because the function is one-to-one. And then how do we find the inverse? So what I've done here is actually this. Going back to section 12.1, in order to find the inverse of a function, if you remember, we switched the x and the y. It was a two-step process. We switched the x and the y, and then in step 2, we solve the equation for y. So that's what I'm going to do. And in our first step, I'm going to switch the x and the y. Remember, the equation we started was y equal a to the x. So you swap out the x and y. So x is now on the left, y is the exponent. Now at this point, just switching the x and the y creates the inverse function. So this is the inverse function. But as I mentioned earlier, this is what we call the implicit form of the inverse function. Okay, and that's what that is, the implicit function. What the implicit form means is that y is not solved by itself. Okay, so it's not solved by itself. It is still mixed in with x. Now we would like to get y by itself. So how do we do that? And here's what I'm talking about, implicit form. Now, in order to solve for y, it turns out that I can't really solve for y, because adding, subtracting, multiplying, taking roots, none of that stuff's going to help me solve for y. And at this point, what happens is really something interesting. Instead of solving for y, this equation, the implicit form, is actually redefined. And that's what's going to happen right in here. We're going to redefine this. And here's how it's redefined. Very interesting. There you go. The birthplace of logarithms. So instead of writing x equals a to the y, the mathematicians thought, well, let's write using this notation. We're going to call y as the logarithm of x in base a. Okay, now, and this is how, in fact, we're going to read this. We're going to read this expression as log, or logarithm, base a of x. So the base of this logarithm is a, x is the argument, x is in here is the argument. And that's how it's redefined. Now, something interesting that we actually note is the following. If you recall, this is the graph right in here. This is a graph of a to the x. We also mentioned in section 12.1 that the graph of every function and its inverse is going to be symmetric with respect to the line y equal x. And that's this line actually, right? So we can actually use reflections to get the graph of the inverse. So for example, the reflection of this point about this line, if I continue going on, the reflection here is going to be right in here. The reflection of this point is going to be about here. The reflection of this point, which is the y-intercept, now becomes the x-intercept, is here. And the reflection of, let's say, a point that is actually on the negative side. So I'm looking at, let's say, a point right about here. The reflection of this point about this line is going to be right around here. Okay, so we actually have the graph of the inverse. And then I can, of course, graph this inverse function by connecting these dots. See that? And that's how the graph is done. But we need a mathematical expression for it. And again, the mathematical expression is that of log base a of x. Now, you think about these things, right? Well, it actually turns out, let me go a little bit on the tangent here for you, but it's for the good reason. So, what's the meaning of logarithm here, right? Whoever came up with this, which I'll explain who came up with the idea of logarithms. The literal meaning of logarithms. Well, if you look at the Latin, early 17th century Latin, logarithms are called logarithms. The Greek of the same thing, of logarithms, it's actually two words. It's made up of two words. And the two words are logos, arithmos. And I have it in red. When you do a juxtaposition, right? You do a juxtaposition of log, L-O-G, and A-R-I-T-H-M portion of arithmos. That makes it logarithm. When you juxtapose those two together, you get logarithm. Now, the literal meaning of logos means ratio. Arithmos is numbers. And in fact, the word arithmetic, we talk about arithmetic. Arithmetic means working with numbers. So there you go. Logos, arithmos, put together, called logarithms. Now, who actually discovered logarithms? The mathematician John Napier, early 17th century mathematician, actually came up with the idea of logarithms. And he actually developed the idea of logarithms in a whole different way, not the way at all that we're doing it today. But he spent nearly 30 years of his life developing the table of logarithms, and his intention, of course, was to be able to multiply huge numbers, astronomical numbers together. Remember, back then, early 17th century, there was no computers or calculators. So a lot of things got done. Almost everything was done by hand. So, and those table of logarithms, which Napier actually discovered, Kepler used them quite often, used his tables for his reckoning. Now, something interesting that Napier has put together is called what's known as Napier's bones. Okay, and that's what this machine is. It's called Napier's bones, and it's actually like an abacus. It's actually kind of like that, but except it's used to do multiplication. It's very interesting, and you can read about this in Wikipedia if you like to. Just type in Napier's bones, and this will come up. Anyhow, let's move away from this. So let's actually find the inverse of 2 to the x. So how are we going to do this? Remember, we're going to switch the x and the y, and that's what I've done here. I've switched x and y. And that gives me x equals 2 to the y, right? But then we don't want the implicit form, so we're going to turn that into its logarithmic form. And in logarithmic form, it's going to be log base 2 of x. Now remember a couple of things here. Let me just highlight these for you. The base in the exponential form here of the inverse, the implicit form of the inverse, the base is 2, and so is the base here. You see that? And in fact, one way to understand log base 2 of x equal y, what does that mean? That means x is the number that you get when you raise 2 to the y power. Okay. And as far as the graph goes, so this is like the graph of 2 to the x, and if you do a reflection of the graph, there you go, we get the graph of its inverse, which is log base 2 of x. And that's the relationship between the exponential function and, of course, its inverse, now logarithms. Now it turns out that these two functions, by the way, are inverses of each other. So the inverse of exponential functions will be logarithmic functions, and the inverse of logarithmic functions will be exponential functions. And of course, here's that line y equal x, which all functions and their inverses are symmetric about. Okay. Now, as far as again the anatomy of the logarithm goes, what sits in front of letter G, log, in this case x is called the argument of the log, and the argument of a log, by the way, has to be positive. And you can see that from the graph. See right in here, this is all positive. The graph is only defined here. You see that over in this segment. The graph is only defined to the right of 0. There is no graph on the left for the inverse, that is, for the blue curve. Okay. And let me remove this part. And the base of the logarithm is a, and base must be positive, and it cannot be 1. We had the same restriction on the exponential function in previous section, if you remember. Now, this is from your book. What does it mean, log base a of x? The meaning of logarithms. Now, one thing that's important here, when they say the meaning of logarithm, that to me, that means that in order to understand what the heck this means, you translate it. So if you translate log x base a or log base a of x equal m, what the heck does that mean? Well, it means a to the m equal x. And that's the only way we can understand logarithms, folks. Okay, that's the only way we can understand them. Now, this next idea here that I have highlighted in here, a to the log base a of x equal x, this one, as you can read, log base a of x is that unique exponent for which when you raise a to the log base a of x, you get x again. Okay, so that's what that is. Now, let's actually go through a few exercises here together, and we're going to see how we're going to actually put this together and how we're going to work on this. Once we go through a few of these, I think the whole idea of logarithms become much more manageable and easier to comprehend. Remember, the key relationship that we have here is what it is again highlighted in here. Log base a of x equal m. What does that mean? It simply means a to the m equals x. So, in exercise 14, question reads, simplify. Now we are given log base 10 of 100, and they say simplify. What does that equal to? So instead of x up here, we have 100, and the base a is 10. The question mark, you can say that's what m is in the general form. So this means 10 to the power of the answer should equal to the argument, which is 100. So we're going to say 10 to what power equals 100. That's the meaning of the logarithms. Remember, logarithms are exponents. It's just the way they were redefined and rewritten. So the answer to this, making a long story short, the answer is simply 2. That's the answer to log 100 in base 10. And there you go. Now, our next question, number 22. We want to simplify log base 5 of 125. What does that equal to? This time again, I'm going to redefine it, just like the translation of logarithm goes. 125 equals, the answer is the base 5 raised to the power of the answer. That should equal 125. So 5 to what power equals 125? And if I rewrite 5 cubed, 125 as 5 cubed, you can kind of see that by inspection. The question mark must be 3, right? And of course, we don't use question marks in mathematics, right? Anything we don't know, we're going to call it x. So later on, we're going to do away with the question mark, and we're just going to put x, the variable for it. So the answer to this one is 3. And another example, number 24. This time the base of the log is 9. The argument is 1. We want to know, what does log 1 in base 9 equal to? So again, this means 9 raised to what power equals 1. And again, by inspection, we know that if any number to 0 power is 1, correct? any non-zero number to 0 is 1. So the question mark must be 0 because 9 to 0 is 1 by inspection. So the answer is going to be 0. Now, something interesting, we can actually generalize what we just found here, what we just did in that exercise number 24. So in exercise number 24, we did log of 1. In general, log of 1 in any valid base means a must be positive and cannot be 1. The log base a of 1, again in any base, log of 1 in any base is 0. And we're going to keep that as a property of logarithms. Let's move on to the next one. Number 26. In number 26, we're doing log base 3 of 3. Now here we have 2 3s, so I've highlighted one of them. Guess I could have used my pen to use a different color for that. And if I did, in fact, let me do that. So I don't know if this is going to mess things up, but that's okay. I'll fix it up. So I'm going to make this a red 3. And also, therefore, let me erase this one and turn that into a red 3. So there you go. Since we got 2 3s, I want to make them distinguishable 3s, right? Because both of them are 3s. So this 3, which is the base, 3 to what power equals 3. That's the meaning of logarithms. And again, by inspection, the exponent must be 1 because 3 to the first power is 3. So the answer is 1. Now note this time the argument of the log and the base of the log are the same, and the answer is 1. And of course we have the generalization of this one. We can generalize this into a property of logs. In general, if the argument and the base of the log are the same, the answer is going to be 1. And right in here, that's the answer. The one above, the answer is always 0. Okay. And let's see, I think they use green, right? So let me use that. I'm going to write this equals 0. Okay. So log 1 in any base is 0. And log base a of a is going to be 1. That's what those are. And we're going to move on. In exercise number 38, now this one is 6 raised to the log base 6 of 13. Now this is simply 13, right? And I have the property in front of it, which we had earlier, where we had the definition of logs. Let me go back up. There you go, right in here. Highlighted in red, right in here. So I'm just using that property. And using that property, the answer is going to be just 13. Right? That's what this is going to be. That is 13, so the answer is just that, 13. Okay. Let me fix that up. So this is going to be 13. And we're done with this one. See, pretty simple. Number 50. In number 50, the question reads, we have y equal log base 8 of 10. The question reads, rewrite in exponential form. So, by meaning of logarithms, log base 8 of 10 equals y. That means, remember the definition of logarithms, this means what you see here now. What's in here? Sorry, I'm not sure what happened. What's in here? That means 8 raised to the y equal 10. So y, again, the answer to the log, y, is the power to which you raise the base to get the argument. And this is just a rewrite, so we're done with this one. We are not solving or anything. Number 56, the same thing. Again, I'm going to say the answer to the log is the exponent to which you raise this base, right? Base raised to that exponent. And it's going to give you the argument, which is 3. That's the rewrite. Number 60, log base m of p equals a. Redefine it. M to the a power equals p. Now in number 66, we're actually going to do the opposite. We are given now the exponential form, and we want to write the logarithmic form. So 10 to the 4th equal 10,000. Write it in log. We're going to put it back in this form. Remember, the answer to the log is the exponent. The answer to the log means I'm down here. The answer is 4. The answer to the log is the exponent to which you raise the base. The exponent, it means 4. To which you raise the base, that's base 10. And that's what's up here. That's the exponent to which you raise the base to get equal the argument. That's 10,000. Argument is 10,000 here. Okay. And that's what that is. There you go. That 10,000 goes right in here. And that's just the rewrite. Let's move on. Number 78 to 1/3 equals 2. The rewrite is log base 8. One thing you probably noted here is this. Whatever the base and exponent will be exactly the base of the log. Look at the one above. Base of the log, base of the exponent. Look at the one above. Base of the log, base of the exponent. Base of the log, base of the exponent. They're always the same. So the only thing that remains is the exponent here in number 70. The exponent is 1/3, and that's the answer to the log. And the 2 that's by itself becomes the argument of the log. We're done with this one. And the last one in that segment of the exercise, y to t equal x. Again, base is going to be unchanged. Base is y, base is y. The exponent on y goes on the other side of equal sign, and x has nowhere to go but in the argument of the log. This x can only be in the argument of the log. And we're done with that segment. Now, we're getting ready to do the last segment almost, and then we look at some of the graphs of logs in Desmos. So this one is the principle of exponential equality. And essentially what it says is this. Let's say we have an equation, exponential equation. Both of those have exponents, one on either side. The bases, these bases, b, are the same, and the exponents are m and n. Well, because of the one-to-one, due to one-to-one property of exponential functions, we can actually say that b to the m equals b to the n, therefore m and n must be the same. So in other words, when you have an exponential equation, which is what this is, if the bases are equal on either side, the exponents must be the same or equal. That's what this says. Now, let's take a look at this exercise. In this segment now, they're actually asking us to solve these equations. So in exercise number 80, we want to solve log base 4 of x equals 3. So what I've done in this next, right next to it, I actually rewrote this expression in exponential form. So the exponential form is going to be 4 cubed equals x. And this practically solves itself. Then almost all of your logarithmic equations are solved by redefining them in the exponential form. You don't have to do anything else. And I did. So 4 cubed is 64, and that's going to be the answer to this exercise. Okay, so there you go. X is 64. There. Now, because the argument of the log, the x, has to be positive, we just always do a cursory check, make sure the answer is positive. That is not the answer being positive, but the argument. And that means this x here. The argument has to be positive, and it is positive. Let's take a look at this one. Now for this one, we actually have number 88. For this one, log base 2 of x equal -1. So again, I rewrote it as 2 to -1 is equal to x. And 2 to -1 by negative exponent rule, that's just 1/2, right? That's 2 to 1 over 2 to the first power, which is 1/2. So the answer is 1/2. And again, the argument is positive, so we're good with this one. The next exercise, number 82. Log base 5 of 25 equal x. And the way I pick these exercises, I'm trying to pick them so where x actually appears on different sides and different portion of the logarithms. So in number 80 and 88, x was the argument. Number 82, x is actually the answer. So we're going to rewrite this as 5 to the x equals 25. And if I think of 25 as 5 squared, and using this principle of exponential equality that's right up here, above here, this principle, we can say x and 2, these must be the same. So x is 2, and that's the answer. Now the answer to the log, by the way, the answer, in this case x, could be positive or it could be negative. But the argument of the log means what's in front of it. Okay, the argument of a log is x. This is the argument of the log. The argument has to be positive. The answer, however, could be negative or positive. It could be 0. The answer could be positive, negative, or 0 if x is 1. Okay, number 86. In number 86, we have log base x. Notice again, this time x is in the base. So we're looking at different dispositions for x. Log base x of 9 equals a half. Rewrite this in exponential form. And again, x to 1/2 equals 9. Now x to a half. At this point, you can square both sides of this equation to solve for x. Or I rewrote x to a half as square root of x, just kind of keep in check from chapter 10 so we don't forget the radicals. There you go. And then solve this by squaring both sides. So x becomes 91. And remember, this time the base of the log has to be positive, and it is. And it cannot be 1. And it's not. Not in number 86. Number 84 is kind of like that. X is the base again. So I rewrote this as x to the first power equals 12. And of course, x to anything to the first power is itself, right? So x to the first power becomes x. And the answer is just 12. And we solved number 84. Let's take a look at now some of the graphs. The graph of logarithmic functions. Now, in order to graph this by plotting points, I started with log base 2 of x. And I actually picked some smart points for x. Okay, so instead of like -2, -1, 0, 1, 2 like that, I picked numbers that are in the domain of the logarithm. Remember here, x has to be positive. Keep that in mind. The argument has to be positive, so I did not pick negative numbers for x. I picked 1/2, 1, 2, and 4. Okay, half, 1, 2, and 4. And then here I'm plugging in for x. Log of 1/2 base 2. What does that equal to? Well, by definition of log, that means 2 to the question mark should equal a half. That means 2 raised to this power should equal 1/2. Now, I rewrote 1/2 as 2 to -1. And the reason I did, because now I have actually an exponential equation, and I can use these and the principle that we had up here. Oops, sorry. This one, the principle of exponential equality. I can use it here. I have 2. Oops, sorry. That got rid of that altogether. Okay. And here I have 2 and I have 2 here. Bases are the same, so exponents must be the same. Therefore, the question mark has to be -1. And that is the answer to log base 2 of 1/2. So that's how I got this -1 in the y column. Then I plug in the 1. Remember, log of 1 in any base is 0. And here's why. Because 2 raised to the power is 1. To that question mark is 1. So that must be 0. 2 to 0 is 1. That's how I got 0. Then I picked x to be 2. Well, log base 2 of 2, base 2 of 2 is going to be 1, right? That was the property we had earlier. And then I picked 4. Log base 2 of 4 is, what does it equal to? And I rewrote by definition of log at 2 to the question mark equal 4. So the question mark must be 2. And that's how I completed this table that you see in here. Okay, this table. Now, and then I plotted the points. So I have 1/2 -1. 1/2 -1 is going to be, see, when x 1/2 -1 is actually right here, that point. It's this one. That's 1/2 and -1. And then I have 0.10. This is actually 10 right in here. Okay. And that's this point. That's 10. My next point was 2,1. This is 0.21. And then it was 8. Oh, I'm sorry, not 8. It was 4,2. And x is 4. Y is up 2. Let me do this. Get rid of that one. Let's see, 4,2, not 8. Okay. So when x is 4, y is up 2, and that would give me this point right here. And then I can kind of draw right through these. Let me use a finer pen. This is going to be the graph. It actually, when x is 8, y would be 3. So something like this. Sorry. And I'll go to Desmos and we'll look at a much better graph of these. But it looks kind of like that. That's going to be 8, 3. And I know because log base 2 of 8 is 3, since 2 cubed is 8. Okay. So we have the graph of logarithm. And that's what it looks like. Okay. Now, let me get rid of this portion of it. This one, I want to get rid of that. Okay, and sorry, my pen isn't cooperating. Now it is. I erased the L. Okay, we're good. Alright, so hopefully you follow that one. Now let me go up. And we're going to generalize now what we just saw here. Okay, so to generalize now, I can say in general this is true. For log base a of x, okay, for log base a of x, if a is greater than 1, then this is the general shape of the logarithms. Okay, it's going to look like so. It's going to look like this, what you're seeing here. It's going to be an increasing function. Function is increasing. The y-intercept now does not exist. What used to be the floor for the exponential function becomes like a wall that cannot be touched nor crossed. Okay. And the x-intercept is at 1, 0. There is no y-intercept. The graph will not touch nor cross the y-axis down below. The function is increasing as you go left to right. It's always rising. And the domain of this function, the domain of the function is going to be the red line, all, well, 0 to infinity, not all real numbers, right? The domain actually going to be just this part right in here. That's going to be the domain right in here, okay? And let me paint it again. This is the domain. And the range is going to be negative infinity to infinity. So it can be anything on the y-axis. That's the output of the logarithm. This function is also 1 to 1, and the vertical asymptote is now the y-axis. The y-axis has equation x equals 0. And those are the properties of logarithmic function. Now, what if the base of the log is not greater than 1? It's between 0 and 1. Well, between 0 and 1, this is what the graph's going to look like, as I've shown you. Has the same properties that it did before, right? The difference is that this is now a decreasing function. Okay, and you can see the decreasing nature of this function. As you go from top to bottom, you see that it's dropping. Other than that, it has all of the same properties as if the base is if the base is greater than 1. So it just changes the direction, the way it's going. Now, we're going to go to Desmos and actually graph these 6 functions, and hopefully you see the general pattern of what this is going to look like. Now, let me see, actually, we're doing, I see. Since we're doing logs, and let's not do 2 to the x, 3 to the x, 4 to the x, actually, I'm going to change that, okay? And we're not going to do that for base a greater than 1. So let's actually do log base 2 of x, and then we're going to do like log base 4 of x. Then we're going to do log base 10 of x. How's that? All of those a's, the bases, all of them are, each of those are greater than 1. All of them. And rather than doing these 1/3 to the x, 1/2 to the x, 1/4 to the x, instead of doing all of these, let's actually do these other ones. I'm going to make the base log. Let's go 1/2 of x. And then separately, we're going to do log 3/4 of x. And then we're going to do log, let's do 1/4 of x. How's that? So those are the ones we're going to do again. So we're going to do log base 1/2, 3/4, and 1/4. And the other ones were 2, 4, and 10. So with that, I'm going to go now to that site, Desmos. Okay. And I already have the site up and running. There you go. So first we're going to do log base 2, base 4, base 10. So I'm going to go log, and let me pause this for a second. Okay, everyone, we're back. So I was going to graph some of these logarithmic functions for you. So let's begin with the ones that have bases that are greater than 1. So I'm going to go log and put the base to, in case you want to do this in Desmos, by the way, in order to input the base of the log, you have to hit shift minus. That gives you a subscript type action. So I'm going to go 2 and then right arrow to get out of that and type x, and there you have it. This is going to be the graph of log base 2 of x, and if you enlarge it, you kind of see what's going on. And you can actually slide, let me see, click on tool, projector mode. It makes the graph looks better, to makes it readable better. And there you go. If you actually drag on the graph, left click, hold and drag, you can actually read these points. And this is 1, 0. Remember, all logs go through 1, 0. So that's what this one is. Let's graph another one. This time I'm going to go log shift minus. This time let's go log base 4 of x. And there you go. You can actually change the color of these if you like. Let's see, image. Oh, no, I didn't want to do that. Sorry. Anyway, let me not mess around with that. Let me change this to, if I get out of projector mode, things will get better. There you go. And next I'm going to look at log base 10. Log shift minus base 10, right arrow to get out, and there you go. So you can kind of see now what's happening with the log function. For base that's greater than 1, remember we started with actually this one, the first one. This one is log base 2 of x. And then this one is log base 4 of x, the one in the middle. And the green is log base 10 of x. So as the base increases, the log looks like this. This is what the log will look like. You can kind of see the effect of base on the graph of the log. I'll show you another one I put together for the effect of base on the logarithms, and that really puts everything in perspective for you. Now let me change the base. Now I'm going to go to a base that is actually go shift minus base. I'm going to go bases 1/2, 3/4, 1/4, right? So let me go with 3/4 first. Oops, sorry. 3. There you go. 3/4 and just put 0.7. Log shift minus 0.75. That's 3/4. Okay. Instead of log base 4, let me go base 1/2 now. That's 0.5 of x. And then we're going to go log base 1/4. Okay. And that's 0.25 of x. So now you can see on this side over here, you can see the effect of the base as it gets closer to 0. So all 3 bases I've picked here are less than 1. So this first one is going to be base 3/4. The one in the middle is base 1/2, and the one in green is base 0.25. So as the base approaches 0, you can kind of see how this thing is behaving. This is what the graph of logarithm looks like. Okay, now let me show you this one. This one very nicely puts it all together now. So here's the log in any valid base. Remember, base has to be positive. And for this one, I made it between 0 and 10. Now, at 0, log base 0, we said base cannot be 0. So there you don't see a graph to the right. Now, let's actually increase a, and now you see the beginning of the log. This is log base 0.1. There you go. That's log base 1/10. And then I'm going to change that to, I'm going to slide it here to 0.2345. Sorry. And we can actually, there you go. You see how it's behaving now? This is log 1. Base 1. Remember, base cannot be 1. And you can see why now. There is no graph when base is 1. Okay. And because we don't have an exponential function at that point. And at 0, remember, it's simply undefined. Log base 0 is undefined. No graph at 0, no graph at 1. Now, look at as we increase the base now. And let me maybe shrink this so you can see a little better. Okay. And right in here, I'm going to increase the base. Look at this graph. See how it's behaving as base gets bigger, bigger, bigger. And here, it's getting smaller. Pretty cool, huh? And let me try it now. I want to make it to where it stays and you can see better. There you go. You can see that branch. You see how the branch is behaving for different values of the base. So anyway, just want to show you what it looks like. This is what log base 10 looks like. Excuse me. And there you have it. So that's all I wanted to show you on the logarithms. And with that, we are done with this section.